Hello and welcome everybody. So today we're in the beta test of Logic World, and I'm in the most recent version, and I'm showing off a multiplier that I built a while ago, but I'm finally deciding to make a video on it. Alright, so the idea here is, let me turn off the inputs here. Whoops. Actually, I'll just make all the inputs something easy. So I have 15 in one input and 15 in the other input, and here's input A and then there's input B. And so the idea here is, if you make a AND gate table of all of the half products, you can then sum all those half products together to get the final product. So the way it works is like 1 times 1 is 1, and there's only one way to produce 1, it's here, and then that literally just goes out to the output, because there's only one way to produce 1. And of course I wanted that to be synced with my adder, so I added delay, so whatever. Okay, but then if you had like 2 times 2, 2 times 2, there's two ways to make 2 times 2. There's two ways to make 2 times 1. If we had it on this first side here, or if we had that same value on top here. Because on these vertical columns it's the same value, so here's the value 1, 2, 4, 8, 16, yada yada all the way up. So you can see that the value 2, there's two ways to make it. 1 times 2 and 2 times 1. Then we move on to 4. There's 3 ways to make 4. 1 times 4, 4 times 1, and 2 times 2. So you just wire them up in a grid like this, and it does all of those combinations for you. So the idea here is you just make a complex, or you make a table of all the values that can be half products just by where they are, and doing the shift allows you to just line up all the values like that, so they're all easy to be worked with. Since all of these are the same column, if you just pass all those columns through the same way through, you keep all the data in line and you don't lose track of anything. So we can see that 16 here, or 2 to the 16, has the most amount of ways that it can be made, which happens to be the most significant bit of the multiplier. So there's a bunch of different ways to turn on the most significant bit, or like the middle bit, I guess, of the result, because it would come through up here. Okay, so let's actually look at how it works. So if I have 15 times 15, what it does is it takes 15, which is 1, 2, 4, 8, plus 2, 4, 8, 16, plus 4, 8, 16, 32, plus 8, 16, 32, 64, and adds up all those values. And that's how it does 15 times 15. Although it doesn't look like, oh yeah, there it is. Yep, this is the result. So it's 224, which is 128 plus 64 plus 32 is 224, plus 1 is 225. So there's 15 times 15. If we wanted to, we can bump it up to 8 by 8. 1, 2, 3, 4. So now we're doing 255 times 255, and now we get whatever that is. So here, let's pull up a calculator result. Okay, so if we do 255 times 255, we get that, which happens to be that in binary. Let's see if that's what we got. So we have to look at the number like this, and then I'll pull back up that calculator. So the calculator says 4 ones in a row, which we got, then 3 ones in a row, which we got, then all zeros and then a 1. Well, look at that, we got that. And so that's that result. So now if we do, what happens if we type in hex the number FFFF, that happens to be 65535, so we're going to do that times 65535. And that's what we're going to do next, and that'll be our next result. So to do that, we will do this. We'll do all these bits, and then we'll do all these bits. We'll make the largest number this thing can actually produce, which is like 4 million something. So here it is, and we'll look at it like this. And the reason these squares are here so you can split it up in terms of every 4 bits, so it's easy to read in hex. So the results we got was FFFE. So, oh, whoops. Yeah, well, it was FFFE0001, and we have FFFE000 and then 1. So if we type that in, FFFE0001, that is the value 4 billion. Wow, never mind. 2,294,836,225. So that's right. So this is like 32 bits is up to 4 gigabytes of addressable memory. So yeah. So this is just under 4 billion, or just above 4 billion, I guess the number is. Yeah, 4.3 billion. Okay, so now back to how it works. Since we have all the values lined up here, we have the value 1, and there's nothing that adds to 1, we pass it through. Then we have 2, 4, 6, 8, all those, and then those line up with this row above it. So if we just add that down, we collapse that row. So basically every 2 adjacent like this, we collapse it down, and then I bypass one of these through to the next adder stage. So bypass the least significant bit through to the next adder stage, and then collapse down the rows. So if we have 16 rows like this, we then have 8 adders. 1, 2, 3, 4, 5, 6, 7, 8. That collapses it down to 8 outputs here. So we started with 16 outputs, now we have 8. But the width of these numbers have increased a little bit. Okay, so now that we have produced a row of 8 outputs, now we take those and sum them together again. So then we have 4 adders to sum 8 inputs. We need 4 adders, and then we get 4 outputs. 1, 2, 3, 4. That then comes to 2 adders, which then comes into the final adder here. And then most of these you don't have to pass through the adder because there's no second input, so you just delay them the amount of time of the adder. And since I'm using these are instant carry adders, they don't grow in size with bits, and they're always 2 ticks in delay. 1 tick for the propagate and carry calculation in parallel, 0 ticks for the carry, 1 tick for the final XOR with the carry and the propagate. So that's 2 ticks right there, because the carry calculation is synchronous and instant with the use of relays. And just like that, we're able to have a full multiplier that's able to multiply literally 65,000 by 65,000 and produce 4.3 billion as a result. And it does this in, well, since each stage is synced at 2 ticks, 2, 4, 6, 8 ticks, plus 1 tick for the input here. And you could use relays here, which would pass one input through synchronously and the other input would toggle it through. But I don't like that because then both inputs aren't synced when this AND gate has both inputs synced here. So I think it's just easier to use an AND gate here and just incur the 1 tick of delay on both inputs instead of a relay which would have 0 ticks of delay on one and 1 tick of delay on the other. So this is 9 ticks latency, but the throughput that you can have is theoretically 1 tick. Every tick you could pass a number through this because these are 1 tick pipelineable, the carry is synchronous, and these are 1 tick pipelineable. So since each adder is 2 ticks, you can compute 2 numbers in the adder at a time because they're 1 tick capable devices. It's not like Minecraft where things burn out at 1 ticks. So you can have 2 numbers in here at a time, so 2, 4, 6, 8 numbers, plus that is 9 numbers, so the amount of delay is the amount of numbers you can have in here calculating at the same time. So I can have 9 numbers in here calculating at every tick, and so that even though it takes 9 ticks for it to come through here, I have 9 numbers that come out, all at the same, all synchronously through. So you can really, it's called pipelining. You can fit a lot of data through this thing really quickly. And so now to show that off, This doesn't quite fully do it justice because the clock speed is a little slow, but actually if we do that, I just up the clock speed, yeah. So basically what we're doing here is we're saying if this is off, then it would allow this to infinitely run, and we have a delay of one of these inverters, 1 tick here, 2 tick here, and then back into the inverter. So there's a 3 tick clock that I can enable. That 3 tick clock will then update these D flip-flops in the counter, which will then increment the counter. And since the counter is 2 ticks, it can clock at 3, no problem. Well, it's actually 3 ticks because of this D flip-flop. So even though I said you could pipeline at 1 tick, I can't create data that quickly. So I'm just going to create data at 3 tick and pipeline this at 3 ticks. And then you'll see the output come through. So if I do server, what is the command? Server, I don't remember. I had to look it up. Okay, so after a long and frustrating time figuring it out, going through the help menu, I've got it server simulation.rate, and then you put in the speed you want. So I set it to 5 ticks per second. You can see that this is extremely slow, but it's updating numbers, whatever. You can see that it's changing numbers. And they update synchronously because all the delays are synced. So now I could really crank this up, and instead of running at 5, we can say let's do 400. And you can see it instantly starts going much faster. And now we can't really see how quick these are changing down here, and we can't really bug test to see if this is working. But we do know that we're getting some numbers streaming through here very quickly. So in numbers, they're being calculated in multiple parts of this at a time. So like one number will take up some of these two, another number will take up some of these two, and another number will take up some of these two, because they're 3 tick pipeline, not 2 tick or 1 tick. So it'd be 1, 2, 3 here. Then another number will be 1, 2, 3 there, and another number will be 1, 2, 3 at the output, like that. And so we can actually insert our own data here wherever we want. Rip. If I do, and I can turn that on, turn it off, remove all those. Because this is a counter that's incrementing, it got saved into those D flip-flops the moment I put that data in. And so now you can see we're doing like high order bits up here. And since one number stays fixed while the other increments through, and since it's a high end number, it's going to take a long time for it to start affecting these higher end bits up here. And we can change the speed again. Instead of 500, we can do server simulation.rate. Let's try 1,000. Let's see if that'll work. And that does not work. We have to stop it immediately. Server. Let's see if we can get 500. And this unfreezes. There we go. So 500 works. The base for the game is 300. But if it puts anything in perspective, Minecraft runs at 10 Hz. So we're running at 50 times faster than Minecraft right now. And we get to use the instant carry logic at that speed, which is nice. So yeah, this is just a multiplier I was working on. It can be used for basically anything, and it's all one board, so if you wanted to clone it, you can just do Control G, like that, and you would have the whole thing on a board here, like that. So that is how you do it, and you can place it like that, and yeah, it still works. But it's bugged because it holds the state of the previous when it gets moved, so you have to like update it. Yeah, I think I have to relog for torque. But yeah, there we go. Oh, there we go. It just got placed. That's why. Okay, yeah, the game was lagging while it was placed. Yeah, and then it reset the state when it got placed. Awesome, so that worked well. And you can still use it here. Do 9 times some random number, and we'll shift it up, yeah. Then yeah, cool. Still works, even when moved. Yep, so that's all for today. If you like this video, please give it a like and subscribe, and I will see you guys next time. If you want a tutorial on this, let me know, so I will be making Logic World tutorials a little bit closer to when Logic World is going to release, so I can show you how to make all this stuff, explain the logic behind it, and then obviously this can be compacted a little bit if you cared, but I was just trying to build something that worked really quickly and kind of cool. So yeah, thanks for watching, and I'll see you guys next time.